Hello everyone, welcome to the OneClass channel. My name is Marlon. I'm a second year University of Waterloo student. I'm studying chemical physics with a minor in math. Today I'm going to be working through some high school and college level chemistry problems. If you're in need of any extra homework help or like some one-on-one tutoring, be sure to check out the links in the description. Okay, let's begin. So for our first question, we are told that the molecular mass of helium is 4 grams per mole. The Boltzmann constant is 1.38066 by 10 to the negative 23 joules per Kelvin, and the universal gas constant is 8.31451 joules per Kelvin. Mole and Avogadro's number is given. How many atoms of helium gas are required to fill a balloon to a diameter of 34 centimeters at 61 degrees Celsius and 0.863 atmospheres? So first, let's just write down all of the constants we've been given. Okay, so for our first question, it's dealing with the amount of atoms. And so if we assume that it's an ideal gas, that means that we can apply the ideal gas equation, which is PV is equal to nRT. We can then solve for N, which is PV over RT. And then we can take note that the number of atoms is going to be the number of moles multiplied by Avogadro's constant. And that's simply because if you do atoms over mole by mole, you'll get atoms as your final answer. And so we need to go about finding the values of our variables inside of this equation. And so we're given that the pressure is equal to 0.863 atmospheres. We are not given the volume. And so we need to go about finding that. If we assume that the balloon is a sphere, then its volume will be 4 over 3 pi r cubed. Let's choose r in meters. And so r is equal to half of the diameter. So it's going to be half of 34 centimeters, which is 0.34 meters. And so you get 0.17 meters. And so for our volume, we'll have 4 over 3 pi by 0.17 cubed. And this will give us a volume of 0.020579526 meters cubed. And then now let's convert that to liters, and it will become 20.56909 liters. I chose liters specifically because we were given the the R value in terms of joules per Kelvin mole, and that will have unit consistency if the pressure is in atmospheres and the volume is in liters. And so if we go about plugging everything into the equation, we will have that N is equal to 0.863 atmospheres by 20.56909 liters over 0.08205 liters atmospheres per mole Kelvin. And then, sorry about that, I forgot to give you the temperature. We are told that it is at 61 degrees Celsius. We're going to need to convert that to Kelvin. So it's going to be 273.15 plus 61. And that is going to give us a temperature of 334.15. And here you can just see that I used the R value that would hold unit consistency. So I had liters in atmospheres, so I'm going to have liters in atmospheres in the R value that I choose. And just recall that it's 334.15 Kelvin. Double check that the units are okay. Atmospheres cancels atmospheres, liters cancels liters, Kelvin cancels Kelvin, and it should leave you with mole. As your final answer, you'll get 0.647 mole. And so we know that my number of atoms are going to be 0.647 mole multiplied by Avogadro's constant, so 6.02214 by 10 to the power of 23 atoms per mole. Again, double check your unit consistency. Moles cancels moles, leaving atoms, which is correct. And this will give you 3.899 by 10 to the power of 23 atoms. And that's your answer for part A. Let's move on to part B. So for part B, we want the average kinetic energy of each helium atom. And we know that the kinetic energy can be stated as 3 over 2 times the Boltzmann constant by the temperature that you have. We have been given all of these values, so it's going to be 3 over 2 multiplied by 1.38066 by 10 to the negative 23 joules per Kelvin, and then 334.15 Kelvin. This is the temperature that we're at. And so Kelvin, so again, ensure unit consistency. Kelvin cancels Kelvin. So this will leave us with joules, and it is going to be 692.0213 by 10 to the negative 23 joules. And then let's just write that in the proper form of 6.920213 by 10 to the negative 21 joules. And that is going to be your final answer. You can just write the simple form of this. So this is the average kinetic energy. Next up, we go to the last question. We are asked for the Rms speed of each helium atom, and to answer in units of meters per second. There's a formula for the Rms speed, and it is going to be equal to the root of 3RT over m, where m is the molar mass. And so m is 4 grams per mole, T is 334.15 Kelvin, and our R value is going to be 8.314 by 10 to the power of 3 grams per meter squared over mole Kelvin. I chose this R value for unit consistency. And so now I just plug in all of that. So it's 3 by 8.314 by 10 to the 3 grams meters squared per mole Kelvin, multiplied by 334.15 Kelvin, all over 4 grams per mole. And I'm going to take the square root of all of this. Let's check out our units. Kelvin cancels Kelvin. Moles, so 1 over 1 over mole will become mole, and then you have a 1 over mole here. So these two technically cancel. And then grams over grams, which would leave me with that. And so as my final answer, I will get a value of 1443.46 meters per second. And that's going to be my Rms speed of each helium atom. And that's it for this question. Sorry, this was supposed to be by seconds.